All right, so in part 3, what we're going to be looking at is electric shock and household safety and circuit breakers. So the idea is that households are wired in parallel, as we mentioned earlier. And the thing about parallel circuits, as we were just discussing, is that every device gets the full voltage. So every device pulls as much current as it needs to be very bright or to work in a full manner. So sometimes it's easy to overload a circuit because all your devices, as you plug more and more things in, they draw more and more current from your power supply. So like here's a toaster that's drawing 8 amps, a heater that's 10 amps, a lamp that's 2 amps. Add those together, that's 20 amps. Well, that's a lot of current, and that can make the wires warm. Okay, and since they're in the walls of your house, if you have too much current, then you can actually cause an electrical fire. And that happened to me when I was a kid. My house burned down because of an electrical fire that started by my bedroom. Anyway, so very dangerous. Fortunately, we weren't home. Um, so what they do to stop that is there's a fuse or a circuit breaker to turn the electricity off if there's too much current, right? Because more current makes the wires hotter. So usually that's limited to 20 to 25 amps for a typical home. Okay, now because you have a lot of devices that you want to have on, nowadays everybody has their computer on, you've got a stereo, maybe you've got all the clocks, you've got the lamps, maybe you've got a fan on or the air conditioning. Then what happens is that to make sure that everybody is able to turn on as much electricity as they want, you have lots of circuits in your house that each can carry 25 amps. Okay, so anyway, so you might have one in the kitchen, you've got one that covers the bedroom, you've got the bathroom and the hallway maybe connected, you've got the living room. So every room usually has its own circuit. And then there's some special circuits for things like the refrigerator. Now, as I was saying, to make sure that you don't draw too much current, there are fuses, or there used to be fuses. There's still fuses in small devices. So fuses in small devices, maybe you've seen a box of fuses. Okay, and so this is a small, tiny little fuse here. Okay, and the thing is about those fuses is that they will melt and stop current flowing. And so a lot of electrical devices have those so that they don't draw too much current. So like in your car, you used to have to replace the fuses once in a while. There's still fuses in your car. They don't look like that. But that kind of fuse is kind of a tube, contacts at each end, and then it would usually have a coil of wire. And when the electricity went in and there was too much current, then that wire would melt and the coil would spring it apart, and then it could no longer carry electricity. Okay, so anyway, so those are still very useful. But they have to be replaced. And so in a house, they decided to replace the fuses with what are called circuit breakers. And so circuit breakers, you don't have to replace, you just have to flip them on and off. So let's go look at those. So here's a safety fuse, an old-fashioned one, the kind they used to use in a house. Right here. And so have a little glass top so you could look in. Current would flow through. If it started to heat up too much, then this material would melt and you would be able to see through the window. It would turn black when you looked at it later. And so that would cut off the flow of the electricity. But circuit breakers just automatically switch off, which will show you how. and when there's too much current. Here's a happy electrician, which, by the way, is a well-paid job and extremely desirable and necessary, especially as climate change destroys more homes, flooding, and hurricanes. That accelerates, and so people will be moving. They need new houses. These guys are going to be busy for the rest of your life. So anyway, so yeah, so if you want a good, steady job, or at least a job that definitely is in the growing category, electricians are still a very useful type of person to have. Boys and girls can be electricians. So anyway, here he's holding an old-fashioned fuse, and here's a circuit breaker, and here's the circuit breaker box back here. And if you've never flipped a circuit breaker, I've got one here. They make this really cool sound. So I don't know. To me, it's a memorable sound. It's like, oh, that's a circuit breaker. Anyway, so go flip your circuit breaker. That was just a box of resistors hitting the dirt there. Okay. So what's inside a circuit breaker? Well, there are a couple of different types, but usually what happens is there's a bimetallic strip. Remember we talked about those in the heat chapter, and they curve when they become warm, and they become warm because too much electricity is flowing. So here's the bimetallic strip, and usually the current flows in, flows through the bimetallic strip, up and around the latch, and out. But what happens is that when the current is overloaded, the bimetallic strip bends, that flips the latch, and now current can't travel, right? It's stuck. It's open, a broken circuit. So that's how they work. And so you just have to push that latch back. So you can kind of hear the little springing of the coils in there when you do that. Now, more household safety information. If you have a 3-pronged plug, that's extra safe. The hot and the wire is one of these flat ones, so that carries the 120 volts. The 3rd prong is supposed to be at 0 volts, and that one is actually what's called grounded. So grounding is actually when the wire is carried down into the ground, and that becomes a source or a sink of electrons, so excess electricity, like we were talking about when you've got a lightning rod. Okay, so the same sort of thing. These wires, that wire should be connected usually to water pipes because those go into the ground, and then what happens is that carries away excess electricity. So sometimes there might be an arc between the two blades, but instead it goes to the grounded part, and that carries it down. So you never want to cut one of those off, even if it doesn't fit in your extension cord. Okay, don't cut those off. They're very important for your safety. Now, people can get shocked. I've been shocked a lot being an electrical engineer. So one of the things is that your body has different amounts of potential difference. You feel the shock differently. Humans can't sit on a wire like this bird can because the bird's feet are close together. So even though there is a voltage drop along the wire, the bird isn't going to be sensitive to that. But you would never want a bird or a person, of course, big enough to cross between the two wires because those are at very different voltages, so you would die. Okay, so anyway, here's a table from your book. 0.001 or 1 milliamp can be felt. 5 milliamps would be painful. 10 milliamps can cause involuntary muscle contractions. That's not all bad. If you've ever stuck your finger in a light socket, like me, then the thing is your arm jerks backwards. So that's good. Takes you out of the light socket. So yeah, so that's actually not necessarily bad. 15 can cause loss of muscle control. That usually is kind of bad, especially for people who are, one of the dangerous things to do is go down into a flooded basement if the water is over the outlets. And what happens is that people step in to the water because they're trying to rescue things, and they get electrocuted, and then they fall down. And so make sure that if you're ever in that situation, you see someone falling down, don't wander in after them because the electricity is still on. You have to push them out of the puddle with a pole, or or turn the electricity off at the back of the house where it comes in. You can turn it off. You should be able to. Okay, so you need to know how to turn your electricity off, or at the circuit breaker box, but usually that's in the basement too. Anyway, so 15 can be very dangerous, but 70 is, of course, really bad. That's if it goes through the heart, then that could cause serious disruptions because your heart is an electrical device. So one thing is, if you're drilling into a wall, you're not sure if there's a wire there or not. Of course, you should have turned off the electricity using the circuit breaker box. But the other thing is, make sure you never put both hands out onto conductive parts. People do this. They're like, oh, I'm trying to reach something in back of the dryer. They put their hand on the dryer. They put their other hand down, get electrocuted. The electricity goes through the one hand, through your heart, through the other hand. So what you have to do is make sure you don't touch anything electrical, conductive. You put that hand behind your back while you're reaching with the other one. Then if you do get electrocuted on one hand, it passes down to your foot. It doesn't go through your heart. Anyway, so make sure if you're reaching for something dangerous or you're not sure, one-handed. That's the way to do it. That'll save your life. Okay, tasers are supposedly 3 milliamps, but of course a fun video is the slow-mo guys. And they do one with a taser, which is pretty horrible. And you get to watch the ripples across the poor guys, the volunteers' back. There's definitely muscle contractions going on there. So anyway, so maybe I've heard it's more than 3 milliamps. Okay. Okay. All right, so you don't want to get electrocuted. So again, that one-handed thing is good, but also the reason that we have a grounding wire on a lot of machines that have rotating parts, like your washing machine, your dryer, your blender, your anything in the kitchen that rotates and stuff like that, your drill, if they're moving, then wires can break. If wires break, they may touch the case. If they touch the case, then you could touch it and get electrocuted. So the grounding wire is often hooked to the case, and that carries it down to ground. That's the symbol for a ground, is like an upside down Christmas tree, which I think I drew before, but I forgot to tell you what I was drawing. Okay, so I can't draw it with this stupid pen. Okay, so it looks kind of like an upside down Christmas tree. And that's carrying the electricity away safely. Now, in your bathroom, you probably have a ground fault circuit interrupter. And that is because you could draw enough current in your bathroom. You know, what used to happen was people drop their blow dryer in the sink, okay, or something, or their razor, an electric razor, and they would drop it in their sink of sudsy water, and because they were, putting a lather on their face, and then the razor would fall in the water, and then the people would get electrocuted because they would put their hand in there, and the razor is busy making contact with the sending electricity through the water down the drain. Anyway, pipe. Anyway, so yeah, so bad things would happen. So what they did was they installed a very fast circuit interrupter right in the bathroom. And of course, some devices have those also. So like the end of your blow dryer, right? You've got usually the buttons, right? So anyway, so when it's on, you can test it to see if it's working, but that flips off your electricity if, you drop your blow dryer in the bathtub. Anyway, so it doesn't have to wait for the electricity to be noticed by the basement to flip off. It does it right away. And it works through the power of magnetism, which we'll be talking about in the next section, next chapter. So there's a coil of wire that is an electromagnet. When there's a lot of current through it, it becomes stronger, and it can actually pull the circuit off. Okay, so it shuts down the circuit. And so those are in your bathroom. They're also now required in kitchens, and they're on a lot of devices. Okay, so that's the end of part 3. We're going to do part 4 next.